Combinations. Combinations and permutations are similar, but for permutations, we're taking the smaller group and putting them in some sort of order, or arranging them into first, second, or third place, or president, vice president, secretary. But for combinations, we're not doing that. For combinations, you're just taking a smaller group from a larger group, where it doesn't matter what order you put them in whatsoever. Looking at a card question first, it says a standard deck of 52 cards has 4, do y'all say suites or suits? Suits. Oh, some argument. Okay. 52 cards has 4 suits. Remember, those suits are diamonds, hearts, spades, clubs. There's 13 different cards in each suit. You can see all 13 of them listed. If the order in which the cards are dealt is not important, how many different 5-card hands are possible? We're going to be able to answer this question by the end of today, but we're going to first look at how to do it the wrong way, okay? We're going to first look and see how would we do it if the order did matter. If the order did matter, this would be a permutation. Obviously, they said it doesn't matter, but if it did matter, it would be a permutation, which is what we learned on Friday. A permutation, again, is where you're putting them in a specific order. You want to know what card is first, and then you want to know what card is second, and what card is third, and what card is fourth, all the way up to 5 cards, because it said 5-card hands. So this is what a permutation means. You're putting them in a specific order. So for the first card, you have 52 choices of what card could go there, and then you would have 51 for the next one, because you already used one, and then 50, and then 49, and then 48. Everyone's got calculators. Let's see what that multiplies to. 52, 51, 50, 49, 48. That's a lot of card hands. 311,875,200 different ways to put them in order are first, second, third, fourth, and fifth cards. Again, this is not a combination. So far, this is a permutation, that's what we're doing. However, the order does not matter for a combination. We don't care what card was first, or second, or third, or fourth, or fifth. We just want to group from a bigger group. So whenever you do a combination, you actually take out all the duplicate hands. The reason there are duplicates is because, think about if you have 5 cards in your hand. Okay, so say you have, I'm going to write them down. Say I have an ace, a king, a queen, a jack, and a 10. Okay. If I were to rearrange those cards in my hand and I hold them as a king, a 10, an ace, a queen, and a jack, are these the same hands? Yeah. Yes, these are the same hands. But a permutation counts these as different. A permutation says, no, this is a different order. So we chose a different card first, we chose a different card second, we chose a different card third. So a permutation counts these as separate when they're not really separate. So a combination takes out the repeats, and there's actually 5 factorial repeats, because there's 5 factorial different ways to arrange these 5 cards. You can put 5 different cards in the first spot in your hand, and then you could put 4 different cards, and then 3 different cards, and 2 different cards, and then 0 different cards. There are 5 factorial ways to arrange the 5 cards. So the formula for permutation and combination is very similar, except the combination formula divides out this little factorial amount here. And we'll see that when we look at the formula on the next one. For a combination, again, it's unordered. It doesn't matter what you pull first, second, third, fourth, fifth. It's an unordered group of R elements taken from a larger group of N elements. So a small group taken from a larger group is called a combination. There's 4 different ways to notate combinations. Look at all these. These all mean the same thing. We used the first one in Algebra 2. I think the last one is used in stats, this N over R looking thing here. The N is always going to be the larger group that you're choosing from, not farm. Larger group. The R is your smaller group. You'll plug them into this little formula. If you remember, this formula looks very similar to the permutation formula, except there's one tiny little difference. Anyone know which part of this formula is different for combinations? They are factorial. This little part right here is what makes it a combination. Without this, it's a permutation. So permutation, combination, permutation, combination, permutation, combination. That's all that's different. Combination divides out those extra ways to arrange it. Let's try one using our formula. There's 14 students on the student council. They decide to select a research committee of 3 students to research how the students are using the school library. How many different committees could they assign from the student council? So are we taking these 14 and putting them in different places, first place, second place, third place? No, we're just choosing a group of 3. I think about it as like a claw machine. Your claw goes in, it grabs 3, takes them out. It doesn't pick one first and then another and then another. It just grabs 3 at one time. So that would be a combination because the order does not matter. No, so it's a combination. Okay, so the combination, since there's 14 students, we'll say 14, and we're choosing 3 of those. So 14 is your N value in your formula, and 3 is your R value in your formula. So when we substitute that in, on the top we'll have 14 factorial, that's our N factorial. On the bottom we'll have R factorial, so that would be 3 factorial. And then we'll have N minus R factorial, which would be 14 minus 3 factorial. We can simplify the 14 minus 3 and just write what instead? 11 factorial. 14 factorial over 3 factorial, 11 factorial. So remember when we did this on Friday, we were doing a bunch of expanding and canceling things? There's a really easy way to expand this. So I want to expand enough of the 14 factorial to cancel with the larger of the 2 factorials on the bottom. So what I'm going to do is I'm going to say 14 times 13 times 12 times, and then I'm just going to write 11 factorial to represent the rest of them, because I can take this entire 11 factorial and cancel it with my larger 11 factorial on the denominator without having to write out 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then 3 factorial, I could just do 3 times 2 times 1. So the entire 11 factorial is going to cancel on the top and bottom. 3 times 2 times 1 is technically a value of what? 6. And what could I simplify the 6 with on the top? The 12. What would that 12 turn into? The 2. So all I have left is 14 times 3 times 2. Excuse me, 14 times 13 times 2, which is not a whole lot. 364. So small. 364 different committees, unique committees. So none of these would be the same people. They would all be different people. Do okay on that one? Okay. Next one. A student must answer 4 out of 6 essay questions on a test. In how many different ways can the student select questions? So are they specifically saying we're going to answer 1, and then we're going to answer another, and then we're going to answer another, and then we're going to answer another? Nope, they just said group of 4. So would the order matter? No. Nope, it's a combination. So we're going to have 6 total essay questions, and we're choosing 4 of them. Doesn't matter which one we choose, first, second, third, fourth, next, whatever you're doing, you're going to put it away and you're going to follow along. I'm going to let your mama know. Why is he doing so bad? Oh, he just plays on his phone the whole time. Okay, the 6 is going to be our N value. The 4 is our R value. we'll plug those numbers into our formula, which on the top has n factorial, so on the top it'll have 6 factorial. On the bottom we have r factorial, and then we have n minus r factorial, which would be 2 factorial. This one minus this one factorial. So when we're doing our expanding, remember, we want to expand enough of the 6 factorial to cancel the larger of the 2 on the bottom. So we want to expand the 6 factorial just enough to get to what? 4 factorial. So we'll have 6 times 5 times 4 factorial, because then I can cancel with the 4 factorial on the bottom. And then 2 factorial is just 2 times 1, which is just 2 technically. So I'm going to cancel the entire 4 factorial. And then really all you have left is 30 over 2. And what's 30 over 2? 15. I could have canceled that 2 with something on the top, but those numbers were rather small. 15 different ways that I can select 4 out of 6 questions. Alright, we're going to have multiple combinations on the back. A combination and another combination. Is that funny? Multiple combinations. Okay. To encourage library use, I wish this was a real thing. The student council, they install a coffee and juice stand in the library lobby. They offer 5 different types of fruit, 3 different flavors of coffee, and 4 different types of juice. As their opening day special, you can purchase a snack pack that has 2 pieces of fruit, 1 coffee, and 1 juice for $3. And then you'll have to use the bathroom all day because that is a lot of fiber. How many different snack packs can they advertise? There should really be like a muffin or a croissant or something like that, but oh well. Okay. So again, this is actually multiple combinations. So the first combination involves fruit. How many fruits are there? There's 5, and you get to choose 2 of them. 5, choose 2 would be that combination. And then the next is there's 3 different coffees. And we get to choose how many?
1.
Just 1. And then lastly, there's 4 different types of juice. And how many do we get to choose?
1.
4, choose 1. So all 3 of these combinations will actually get multiplied together. It does not multiply beautifully. It's not like we can just multiply all the first numbers and then multiply all the second numbers, but we can expand and cancel where we need to. So I'm going to write out my formula over here again. It's n factorial over r factorial times n minus r factorial. So on the top for the first one, I'm going to have 5 factorial. And then I'm going to have 2 factorial. Bless you. And then I'll have 5 minus 2 factorial, which would be 3 factorial. And then for the second one, what's going to be on the top? 3 factorial. And then on the bottom, we'll have 1 factorial, which is just 1. If you want to write it, you can. If you don't, it's up to you. And then we'll have 3 minus 1, which is 2 factorial, which again, 2 factorial is just 2, because it's 2 times 1. And then for the last one, what's going to be on the top? 4 factorial. And then on the bottom, we'll have our r, which is 1 factorial, and our 4 minus 1, which is 3 factorial. Thinking about expanding. Technically, I could actually cancel one of these factorials already. Anyone know which one I can cancel completely? 1 of the 3 factorials, yeah. Because these are diagonal, you can cancel the one in the middle and then the one on the bottom on the first fraction, or the one in the middle and the one on the right on the last fraction. It doesn't matter. I'm going to do, which one do you want to do, Lauren? The first and the second, or the second and the third? Second and third. Sounds great. So no need to even expand this. For the 5 factorial over here, we want to expand enough of that to cancel what on the bottom? The 3 factorial. So 5 times 4 times 3 factorial. And then on the bottom, I've got a 3 factorial it's going to cancel with. And then technically 2 factorial, I can just write what instead? 2. That's 2 times 1. And then I got nothing on the top of the first fraction, so I'm just going to write a 1. And what do I have on the bottom? 1 factorial times 2 factorial is technically just 2, right? Okay, Okay, and then for this one I got 4, 3, 2, 1, and what do I still have on the bottom? Just a 1, right? So we're going to cancel what we can. I can definitely cancel this 3 and factorial. And then these two, if I were to multiply these together, they would have a value of what? 4. So I could cancel both of these with what from the top? 1 of the 4s. 2 times 2 would be 4. Cancel it with 1 of the 4s. So we have nothing on the denominator left, just 1. And then on the top we've got a 5, a 1, a 4, 3, 2, 1. Which is almost mental math. That would be 20. 20 times 3 is 60. 60 times 2 is 120 snack packs. And several trips to the bathroom. They need to bring that back. We had the coffee bar. Yeah, I miss it. They were, yeah, they used to always leave a mess there. They took it away during COVID. All right, the next question. We're actually going to go back to that very first question that we started with. We never answered that very first question. The very first question said, if the order in which the cards are dealt is not important, how many different 5-card hands are possible? We're finally getting to answer it. This question has a lot of information that you don't need. It says a 52-card deck has 4 suits, hearts, diamonds, clubs, and spades. There's 13 cards in each suit. If the order of the cards dealt is not important, how many different 5-card hands are possible? The fact that they say it's not important, it doesn't matter what we choose first, second, third, fourth, fifth, means it's a combination. Okay. How many total cards are there again? 52. And we're choosing a group of how many? 5. So we have our N value, we have our R value. We're going to substitute those into our formula. On the top we'll have 52 factorial. On the bottom we'll have 5 factorial, and then also 52 minus 5 factorial, 47 factorial. So we're going to expand just enough of the 52 so that we can cancel which part of the bottom? The 47. Snacks? Okay. 47, yes. 52, 51, 50, 49. I'm notorious for forgetting numbers in here. 48, and then 47 factorial to cancel with that bottom 47. It's a good thing we don't have to write that whole thing out. That would be terrible. I'm going to write out my 5 factorial. 5, 4, 3, 2, 1. Okay, and then we'll do just a tiny little bit of simplifying. What all could we simplify? The 5 I could simplify with which part of the top? The 50. Let's see. What is 4 times 3 times 2? 24. Would 24 simplify with anything on the top? A 48, right? You could turn that 48 into a 2. This is just one way to simplify it. It's not like the only way you can simplify it. So left over we got 52, 51, 10, 49, and 2 that we have to multiply. 52, 51, 10, 49, 2. No, 2 million. Did you forget this too?
I punched the 21 instead of 2.
Oh, okay. 2,598,960. This is the number of 5-card hands you could have. This is why you're not going to win when you play poker, guys. I'm sorry to burst your bubble. You're not going to win. The big money hands on poker are going to be like, this is a big money hand. Anyone know what this is called? It's a royal flush. Yeah. Royal flush. Royal meaning it's all the high cards, like basically the face cards. Flush meaning all cards are the same color. How many royal flushes are in a deck? There's only 4 royal flushes in a whole deck. Because you can have all the face cards that are hearts, all the face cards that are spades, all of them that are clubs, and all of them that are diamonds. There's only 4. So I think there's 4 out of 2.5 million. You're not going to win when you play poker, guys. You're not. Don't gamble. Just spend your money. Go buy shoes instead. Alright. Next one is slightly different. In how many 5-card hands are all 5 cards the same color? Believe it or not, this is very similar to the snack pack question. Doesn't seem like it because it's involving cards, but it does have 2 combinations. The first combination involves choosing a color. How many colors are there in a deck of cards? No, there's only 2. Black and red.
Oh, right.
There's only black and red. So there's 2, and how many do we need to choose? We just want to choose one of them. Okay. And then the second part of it comes from how many cards are there of that color?
13.
Hold on. Yes, good job, Lauren. Choose 5 of that color. So Lauren told us if there's only 2 colors in a deck, that means half the deck is black, half the deck is red, which is 26. So there's 26. And we want to choose how many of them? 5. Very good. So this is our tiny little combination snack pack of cards. 2 choose 1 simplifies pretty nicely. It would be 2 factorial over 1 factorial 2 minus 1 factorial. Which, guess what that's going to simplify to? 2. Just 2. This one though, let's see. We'll have 26 factorial over 5 factorial times 26 minus 5 factorial, 21 factorial. Okay. Again, this 2 factorial over 1 factorial, 1 factorial, this is just 2 times 1 over 1 times 1, which is what again? 2. 2 times. And then for the second one, how much of the 26 do I want to expand? Enough to cancel the 21. Factorial. And then I also have a 5 factorial on the bottom. 5, 4, 3, 2, 1. Cancel some things. Let's see. 5 and 25 would do alright. Also, we already know what 4 times 3 times 2 is. What's 4 times 3 times 2? We did it on the last one. 24, which would cancel with the 24 on the top. That's just one way to simplify it. So when you do all of your multiplying, don't forget this big 2 you got at the front. We got 2, we got 26, 23, 22, and a 5 left over. $131,560. That's how many hands would all have the same color. I think it's possible to get that. What is that? I think that's called a flush when you have all cards of the same color. So you're more than likely going to win. I mean, that's not that bad. This many out of this many would be how many flushes there are. Your probability.
That's still a huge difference.
It's still a big difference. But it's better than a royal flush.
What if you have all like two tens?
That's a royal flush.
But like without the
Oh, that's just, what is that called? I don't know the name of the hand.
I guess it's like the royal cards, but they're not.
But the royal cards, but not all of the same color. A full house? That sounds about right. Yeah, that sounds right. Yeah. Don't go home and say Miss Brody told you how to gamble. Don't you dare. Miss Brody told you not to gamble. Alright, for the next section, we're not doing any calculating. We're just trying to figure out whether it would be a permutation or a combination. What is the difference between the two again?
Permutation, the order matters.
Permutation, you're putting them in a specific order. The order matters, right, Sabrina? Uh-huh. The order matters. For a combination, you're just taking a claw machine hand, you're grabbing a group. You're not grabbing one at a time, you're just grabbing a group. For the first one, picking 3 people from a group of 10 people. Combination. Take that claw machine, grab 3, drop them off. Picking first, second, and third place winners at the science fair. That's a permutation. You're putting them in an order. Yep. What if it had said that you're picking 3 winners at the science fair? Right. If it just said 3 winners, that would be a combination because you're just picking a group of 3. Selecting 3 students to attend a conference in New York. Combination. Just picking a group. And then my all-time favorite, selecting 3 numbers on a combination log.
Combination.
It's not a combination. It's a permutation.
Wait, so it does matter then? Oh, it does matter.
It does matter. Think about your locker. You guys have lockers, right? Okay, so say your locker combination is like 49, 12, 25. If you put these numbers in a different order, is it going to unlock?
No.
No. It has to be in this specific order. This number, then this number, then this number. We